Dear ladies and gentlemen, the title of my presentation is The Prediction of Structural Properties of Nickel Titanium Shape Memory Alloy by the Supervised Machine Learning Method. Shape memory alloys, or SMA, are the basis for producing functional materials which possess the effect of shape memory and superelasticity. In turn, to assess the strength and lifetime of structural elements, it is necessary to model the material's structural properties. This task can be solved efficiently using supervised machine learning methods. The aim of this study is to predict the structural properties of pseudoelastic nickel-titanium shape memory alloy, namely the dependencies of stress and strain range on the number of loading cycles by supervised machine learning methods. The dependencies of stress range and strain on the number of loading cycles for the four specimens that were taken from the study SME 2018 were predicted by methods of machine learning in the programming platform Orange. For each specimen, two models were built. On the input of each model, they were given the dependencies of the respective physical quantity on the number of loading cycles. The number of loading cycles was treated as an independent variable, and the physical quantity was chosen as a dependent variable. To increase the accuracy of modeling results, the dataset was augmented. The data augmentation was performed by interpolating the original experimental data by one-dimensional Akima spline. Akima spline is a type of non-smoothing spline that gives good fits to curves where the second derivative is changing fast. For each specimen, the dataset was split into two unequal parts. The training dataset contained 66% of the total dataset. The regression dependencies were built by methods of random forests, neural networks, gradient boosting, support vector machines, OSVM, AdaBoost, and k-nearest neighbors methods. Each of the obtained models was checked additionally by k-fold cross-validation method 10 times. Figure 1 shows the model flowchart, which was built in the programming environment Orange. Table 1 shows specimen number and sample sizes for stress and strain ranges versus the number of loading cycles. Table 2 shows prediction errors and correlation coefficient for delta epsilon and delta sigma built for specimen number 10 using various supervised machine learning methods. As it can be seen from Table 2, the lowest errors for specimen number 10 were shown by AdaBoost and KNN for delta epsilon and random forest and KNN for delta sigma. Figure 3 shows the predicted versus true values of physical quantities for specimen number 13, A built for delta epsilon by means of AdaBoost method, B built for delta epsilon by means of KNN method, C built for delta sigma using random forest method, and D built for delta sigma using KNN method. Tables 3 and 4 show prediction errors and correlation coefficient for delta epsilon and delta sigma built for specimen number 10 and 16, respectively using various supervised machine learning methods. Table 5 shows prediction errors and correlation coefficient for delta epsilon and delta sigma built for specimen number 17 using various supervised machine learning methods. For the specimen number 17, the lowest errors were obtained by random forest and KNN for delta epsilon and delta sigma. Conclusions. There were predicted the structural properties of pseudoelastic nickel-titanium shape memory alloy, namely the dependencies of stress and strain range upon the number of loading cycles, by employing the methods of supervised machine learning. The predicted versus true values of those two chosen physical quantities were built. They are very close to the bisector of the first coordinate angle, which confirms high prediction accuracy. The best results in terms of root mean square error and mean square error were shown by AdaBoost and KNN for delta epsilon and by random forest and KNN for delta sigma. Thank you for your attention.